Good afternoon, everyone, and good morning to those who are joining us from WA, South Australia, and Northern Territory. Welcome to another masterclass webinar by ARISO. My name is Sudha. I'm the GM of Products and Innovation at ARISO, and I'll be your host for this webinar. Before I proceed any further, I'd like to acknowledge the traditional custodians of the land where we meet today. And for me in Perth, that's the Whadjuk Noongar people. I would like to pay my respects to the elders past and present and extend that respect to Aboriginal and Torres Strait Islander people with us today. I also like to extend a warm welcome to the passenger network operators who are participating from all Australian states, New Zealand and Hong Kong, who has joined us, and also the fire safety professionals from various fire departments who are also participating with that. So a special welcome to everyone who are joining us today. At ARISO, we develop standards that ensure hazards in the railway are effectively mitigated. In other words, our standards function as controls to mitigate specific safety risks. Fire safety is a key area of focus for ARISO, and the AS7529 series of standards on rolling stock fire safety is made available to mitigate those risks. These standards are currently under review. The focus of the update is on new net zero emission technologies such as lithium-ion batteries, hydrogen, and ammonia. Earlier this year, we released the AS7529 Rolling Stock Fire Safety Part 1, which are focused on locomotives and freight. There are 2 additional standards currently under review, and we expect that to be delivered later this year. That is the AS7529 Part 3, Fire Safety on Passenger Trains, Passenger, and AS7529 Part 4, Fire Safety on Track Machines. In this focus, today's webinar addresses an emerging risk that is now front in mind across transport and fire safety sectors: lithium-ion batteries, particularly those used in e-bikes, e-scooters being carried on passenger trains. These devices are now part of everyday mobility, and lithium-ion batteries are embedded in many items passengers routinely carry. But the industry is increasingly recognizing that when these batteries fail, the fire behavior differs from the traditional passenger belongings. The onset can be rapid, the heat release intense, and the gases toxic and flammable. In the rail environment, that matters. A train carriage is a confined, occupied space, and an incident can quickly become passenger safety, operational continuity, and emergency response and asset protection issue. Today's webinar will introduce the findings of an ARISO technical paper by the Fire and Life Safety Working Group that examines the fire and life safety implications of lithium-ion battery fires on passenger trains. The work is supported by the ARISO Safety and Operational Standing Committee, and I want to thank their contribution into this discussion. Our presenters will take us into the detail, what the hazards are, where existing controls may be challenged, and what practical strategies operators, regulators, and emergency response may need to consider. Without further delay, let me introduce the presenters. Firstly, Klaus Clemens, Chair of the ARISO Fire and Life Safety Working Group. As a consultant, Klaus has 35 years experience as a consultant executive manager. He started his career in the petrochemical industry before moving into the transport sector. He has been actively involved in the program level in risk management, as well as in the tender, design, construction, and operation of transport infrastructure. Also with us today is Associate Professor David Lang, School of Civil Engineering, University of Queensland. Prior to joining UQ, Dr. Lang worked in the UK and Sweden. He has developed fire safety strategies for laboratories, commercial and residential facilities, and has conducted fire risk assessments and risk engineering projects across a range of industry sectors. Klaus and David, really thank you for joining me and to provide this paper and the findings. Before I hand over, a quick reminder to everyone, everyone in the audience to enter your questions to the team's Q&A, at any time during the presentation, and we'll provide them to the presenters at the end of the presentation so that we can have a Q&A sessions at the end of the day. Over to you, Klaus and David.
Thank you, Sudha. Okay. So let's get this. Does that come up okay?
Yeah, that's come through. Okay, thanks, Klaus.
Okay. Change the page. So just some background on the working group. The working group came out of external interest through our operations working group, and it's all completely pro bono. Everyone involved is giving up their free time, but technically I have to note the huge contribution of Nathan White, David Lang from the University of Queensland, Nathan White from CSIRO, and Lachlan Henderson from Metro Trains Melbourne, all highly qualified fire engineers who've made enormous technical contributions to what we're doing. The other thing I want to point out is that the technical testing that we're planning to do, which is addressing the questions that we've been left with in our technical review, the paper that's available from this work, is supported by Fire and Rescue New South Wales technical labs, research labs, are providing the batteries that we'll use to test on trains, which are provided by Sydney Trains. And more importantly, Sydney Trains has provided us a location and the approvals to do the testing on their site at Chullora. But you can see that we've got most states and territories covered in the working group. And basically, the way the working group works is that if we can't agree on a technical aspect that we think is important or is a gap, then we left it out. So basically, what you have in the technical paper is our collective view of what we think is important to communicate about battery fires on trains. So just moving on to that topic, when we, in the railway industry, when we build a new station or a tunnel, or in this case where we're interested is a train, one of the first things you do as a fire engineering group is decide on the design fire, the fire that train is to produce an acceptable, safe outcome from. Traditionally, that fire has been about 1 kilo of newspaper, basically battery fires, as we know them today, completely exceed what a 1 kilo of newspaper fire would represent on our railways, and I'll talk about that. And David will give you the technical explanation. But the important thing for us as safety professionals is that the railway that we have out there right now is designed for a 1 kilo newspaper fire, and the battery fires are about 10 times bigger and generate a lot more heat and develop much more rapidly. So the battery fires completely defeat our design, and I would argue destroy our mitigations and our controls that we have in place at the moment for fires on train. David's presentation will explain this in a lot more technical detail, but that's basically the position we find ourselves in right now. But at a higher level, and David's going to give you the detail, is the fire is 4 times the size, the fire growth rate is 10 times the size. We haven't got a measure yet of the extra toxicity, but it is extremely much more toxic, and it produces much larger volumes of hot gas than what we've allowed for in our design fires. So this is something that really challenges everything, all the safety arrangements we've put in place, and represents a real hazard to what we're trying to control. So with that, I'll hand over to David, and when David's finished, we'll come back to me and I'll talk about the further papers we want to write out of David's research.
Thank you, Klaus. And hopefully everybody can see my slides coming up now. Can you just give me a thumbs up, Klaus, or just let me know if that's come through okay?
Just a sec.
Wonderful, thank you.
I've got to stop sharing, I think. Oh no, it has already done it for me. Thank you. Yes, I can see your slide, David.
Cool.
All good.
Wonderful, thank you, and thank you everybody who gave me a thumbs up. I'll just very quickly just thank everybody for the opportunity as well. I'm not sure what backgrounds of people I'm speaking to here, so I may dumb things down a little bit while I'm presenting. Hopefully you'll forgive me if you have a bit more of a technical understanding of fire safety here. And before I do continue, I'll also just say thank you to SUDA for the opportunity to present and acknowledge the Turrbal and Yagara peoples on whose land I'm able to continue telling my story. I want to talk about the available decision-making and incident response time on railways in response to fires, and talk about how this might look to a typical design fire. So I've given you a conceptual image here of a 250 kilowatt fire, something which corresponds to that kilogram of newspaper which Klaus was talking about before. And I've given you kind of a nominal timeline for that as well. So evolution of that fire size over time from ignition. And so thinking about how this might evolve inside, or how an incident might evolve inside of a railway carriage based on that 1 kilogram of newspaper. We'll obviously have ignition. At some point after ignition, we would have detection or observation of a fire. Now that detection could be based on some kind of an automatic detection system on board of a carriage or on board of a piece of rolling stock. It's much more likely that there's going to be an observation of that fire, I think, from one of the passengers on that piece of rolling stock. Regardless of how that occurs, that's going to trigger some kind of passenger displacement. Ideally, passengers are going to start moving away from that fire while that train is moving. So going to start to displace themselves away from that fire inside of that rolling stock. They'll hopefully notify the crew, or the crew will become aware of it because of the detection. And that would trigger some kind of a crew response. Now that may involve management of passenger displacement. It's very likely to involve some kind of a decision to stop the vehicle, so a vehicle response to that fire. And then that would be followed by disembarkation of the passengers, so detraining of the passengers. And that should happen before untenable conditions occur inside of that carriage, inside that piece of rolling stock. Now, I've given an indicative timeline of about 10 minutes for this, and that's based on the discussions that we've had within the Fire and Life Safety Working Group. 10 minutes is not an unreasonable time from ignition to full detraining of the passengers after having stopped a vehicle, especially under peak operating hours as well. Could take quite a considerable amount of time. Now, obviously, these passengers are going to be detraining at a station. There's going to be some kind of a station response as well to this, whether this is above ground or underground. And there may eventually, depending on the context here, be untenable conditions within a station. You'll have emergency services intervening to this, and ideally, all of this process should take less than 15 minutes to move the passengers away, which means that your untenable conditions at a station may occur after that. All right. So really nominal times here for your typical 1 kilogram of newspaper fire. I want to take a step back and talk about that 1 kilogram of newspaper fire now, and then give you some examples of different sizes of fires. So that newspaper fire could be characterized in the same way as we characterize this candle. This candle is what we call a buoyant diffusion flame. It's something that in fire science and fire safety engineering, we would be very comfortable in saying that we're able to characterize. Faraday gave a series of lectures on this topic about 200 years ago and gave a very good summary of, or a very good scientific description rather, of how a candle actually works. And the principles of this are similar to most of the fires that we would consider in fire safety engineering. What we've got here is fuel that's produced, which is then vaporizing at the wick, and then diffusing with air, forming a flame sheet where you've got a combustible region kind of in the gas phase there as well. That flame sheet will radiate energy back down to the solid fuel, which is then continuing to move through capillary action up the wick and then diffusing with air again, so vaporizing and diffusing with air there. Now, the products of this combustion process are relatively simple: carbon monoxide, carbon dioxide, water, nothing particularly complicated there at all. We've got buoyancy, which is driven by the energy produced here, the heat energy produced there, which is pulling everything upwards from that. As it moves upwards, it starts to entrain air, which increases the volume of gases which are produced as well. So complicated enough, but something that we've been dealing with as fire safety engineers for quite a long time. And most of the interventions which we have got in place, which are put in place either in the built environment or in transportation infrastructure, are based on this type of fire. Now I can add complexity to this. This is actually a 221 kilowatt fire. I took this from the NIST calorimetry database just to give you an idea of what this would look like as well. So this is a 221 kilowatt fire, similar to that 1 kilogram of newspaper. And you can see as this grows relatively quickly up to that sort of size. So this is what we're designing railways for today, that 1 kilogram of newspaper. Okay. Now I want to show you a slightly larger fire, and I'll come back to the size of this in just a minute. This is an 897 kilowatt fire, again from the NIST calorimetry database. And the growth rate of this is actually pretty consistent with that 250 or 221 kilowatt fire, which I showed you a moment ago. The peak heat release rate, which is one of the terms that Klaus was talking about just a moment ago, it's not quite 4 times the size of that 250 kilowatt fire. But you can see that this larger fire, 897 kilowatts, quite significantly visually larger than that 221 kilowatt fire that I showed you a moment ago. So that's the peak heat release rate from this fire, which is achieved then. Okay, so that's something which is about 4 times the size of peak heat release rate compared with what we're designing railway carriages and rolling stock for today. I want to move on from this and start to talk about batteries and some of the issues with batteries and some of the reasons why we're encountering batteries more and more on transportation networks. Batteries have become ubiquitous throughout our environments. We are finding them everywhere. We've been finding them everywhere actually for a very long time. We're starting to see them in shipping and transportation. So very significant examples in roll on roll off passenger ferries as well as car transporters. We're seeing them in car parks, either underground, above ground, or on car stackers, creating challenges there. We're seeing them in the open road, closed road. We're seeing them in offices and in trip facilities. We're seeing them in homes, warehouses, recycling facilities, and disposal issues around about those as well. In offices and trip facilities, that's one of the most important things when you think about the issues with batteries in rolling stock on commuter transportation networks. The reason for that is that personal mobility devices are starting to be used, or have been used now, more and more as part of first mile, last mile transportation routes. So members of the population, members of the public who live in urban areas using personal mobility devices for the first mile of their commute into work, and then using some form of public transport network, and then using personal mobility devices for the last mile of their route into work as well. So that's part of the motivation why we're seeing batteries inside of passenger rolling stock. Now, I want to talk a little bit about the chemistry of these batteries as well, and why these are so popular devices. So this plot just shows the energy density, or the specific energy, so the amount of energy per unit volume, or the amount of energy per unit mass of different battery technologies. Now, I want to highlight in particular the NMC as well as the LFP chemistry, because they're the most common chemistries of lithium-ion batteries that we do see, I think, in transport infrastructure and transportation products. In particular, NMC. LFP are becoming probably more common, I think, in cars and electric vehicles. NMC still has a lot of popularity in personal mobility devices, but it's just because of the high energy density and a high specific energy of that particular chemistry of battery. Okay, so most of what I'm going to show you for the rest of my presentation is going to be focusing on the NMC chemistry. Okay, now moving into the construction of batteries, most of them followed the same electrochemical principles. So what I've got here is a simple schematic of an 18650 cell. This is a cylindrical cell, which is 18 millimeters in diameter and 65 millimeters in length. Okay. Now, what you can see in the image that I've got on the screen here is essentially just a roll of the anode and the cathode with a separator, a non-conducting separator between them, and then there's some kind of an liquid electrolyte. And all this is kind of inserted into a can, which forms that battery. Now, I've chosen the 18650 cell to illustrate this because this is probably similar to most cells that you're familiar with. Thinking about AA battery cells in particular. So this is an example of 18650 cells. You'll find different numerical indicators for this, or names for this, so people use different diameters, different lengths as well. So the 18650, as I said, 18 millimeters diameter, 65 millimeters in length. So these are cylindrical cells. We also find cells which are prismatic or even pouch cells. Pouch cells probably more typical of what you'd find inside of a mobile phone or a laptop, and prismatic cell probably being typical of what you'd find potentially in an electric vehicle or in your energy storage system if you've got a battery energy storage system at your home. Okay, so these are cells. Now, most batteries are comprised of multiple cells. So this is an image which I've taken from the literature. So this is a piece of work that was published by the Fire Safety Research Institute, which shows an e-ridable or personal mobility device battery with the casing having been taken off. So when we talk about batteries, we're not talking about individual cells. We're actually talking about a lot of individual cells inside of one casing. So this is a battery pack which comprises multiple cells, multiple 18650 cells in this instance. Right? So when I talk about batteries, for most of what I'm going to show you in terms of the videos, I'm going to show you individual tests of cells. I'm going to show you videos as well of batteries, in particular e-ridable batteries. Now, one of the problems with this type of technology, though, is that abuse in different forms will lead to thermal runaway. Now, I've got 3 different types of abuse on the slide here, which I want to talk about. I want to talk about a mechanical abuse, electrical abuse, and thermal abuse. Now, the mechanical abuse is something which you could find occurs under normal use, in particular of a personal mobility device. So maybe there's a collision, maybe there's some kind of deformation if somebody knocks into something or has an accident on their device. Other forms of mechanical abuse include, for example, punctures, and that's one of the most common tests which are applied to batteries, is a nail puncture test. Now, any form of this mechanical abuse could lead to an internal short circuit within a battery. That internal short circuit could also be caused by, for example, overcharging. It could be caused by over-discharging. It could be caused by dendrite formation from repeated charging and discharge cycles of the battery as well. All of that will lead to a kind of, or we term as electrical abuse. Now, that internal short circuit will lead to local overheating. Overheating could also be caused by thermal abuse, so an external heating source applied to that battery. For example, if the battery becomes involved in a fire which starts elsewhere. That thermal abuse will lead to thermal runaway. That thermal runaway will lead to high temperatures, explosions, and flames. Now, interestingly, this point is where most bow ties stop. All right. So if we think about risk management in different contexts, whether that's on railways or in other transportation infrastructure, this point of high temperature and explosion and flame is where most of those bow ties will actually stop. And it was a recent piece of work which was carried out by GHD for ONSER, which really highlights in the bow tie descriptions of how these hazards are managed by railway organizations around the world, that this is where most of those bow ties do stop. Right. So I'm going to show you now what that thermal runaway process looks like. Now, you'll remember the video I showed you, or the image I showed you a short while ago, of a candle burning. That's the sort of fire that we're comfortable with dealing with. This is a single 18650, which we pushed into thermal runaway. If you can see my video, you'll actually see it was actually done here in the lab where I'm sitting, just to the left over my shoulder. If I run this video, this 18650 cell is not significantly larger than the candle. In fact, it's probably a little bit smaller than the candle is physically. And you can see that the type of fire that it produces is significantly different from that candle, that buoyant diffusion flame, which I described earlier. Now, I'll come back to some of these characteristics in just a moment. We've got a lot of experience going back to those use cases, which I mentioned earlier, of the consequences of battery fires. All right, so I spoke about car transporters. We've had several car transporters now which have sunk as a result of vehicle fires. We've got experience of automated storage and retrieval warehouse fires. We've got experience of energy storage systems in buildings. Personal mobility device fires in residential settings, as well as fires in recycling facilities. We're very well aware that the consequences of battery fires can be quite extreme, quite challenging compared with the sort of fires that we might be designing these types of infrastructure, these locations for as well. All right. Now, the reason for that is because of the different characteristics of the fire. This is that same fire which I showed you, that same test which I showed you, but in slow motion. What I want to highlight here is that rather than having that fuel being produced in gaseous form, what we've got here is a solid particulate and gas ejecta being produced at exactly the same time. I've got momentum-driven flows instead of those buoyant-driven flows, which I showed you in the candle just a moment ago. The momentum-driven flows, they occur because of the high pressure that builds up inside of the can of this 18650 cell. Let me just run that video again. As well as the momentum-driven flows, I've got multi-phase reactive flows. What you can see in this video is that the solid particulate is igniting the gases in this ejection. We've also got very complex combustion products, which I'll come back to a little bit later on. Now, if we think about this particular fire in the context of a railway carriage, we actually do have some data on that already. So this video here, what I've done is I've lined up that 1/20th speed video of a single cell going into thermal runaway with a battery fire and a personal mobility device from a train in Barcelona. Now, what I really want to highlight with this is the speed at which the battery evolves into quite a significant fire. So it's around about 17 seconds from the actual initiation of this fire to the CCTV camera inside of this carriage being completely obscured because of the products of combustion. All right, it's a very rapid development to what we would say in different contexts would be an untenable condition. So untenable in terms of visibility being completely compromised over that short distance that we're interested in. So we've got experience of what this looks like on railway carriages. That's from Spain, that's from 2022. We've also got quite a good idea of the size of fires and the impacts of these in different contexts as well. So these two videos which I'm showing here, these are in residential settings. One of them is from Sydney, the other one's actually from London. And what you can see here is actually the size and the intensity of a fire involving a personal mobility device in actually quite a confined space. And you can see actually on the right-hand video, the fire actually manages to get out of the apartment through the gap under the door. And you can see in the video on the left, the magnitude of the fire, the intensity of the fire, as well as the large amounts of solid ejecta and mass which is being produced and ejected from that battery as well. So a very, very significant fire in that residential setting. Now, around about November, the end of November, start of December last year, New South Wales recorded the 100th e-ridable battery fire of 2025. Okay, so the frequency at which we're starting to see, or we're seeing fires involving e-ridables, personal mobility devices, is actually increasing. Early last year, hopefully these do work. Yep, these are working.
Yep, they're good, Dave.
Let me just mute all these. So early last year, I think around about April last year, there was an incident on Melbourne Metro, a personal mobility device fire. On the top right video that I've chosen here, you can see a personal mobility device going into thermal runaway on a station in London. On the bottom left, another fire in London. On the bottom right, another fire in Toronto. Now, I've chosen these videos very deliberately because they show an incident in Australia. They show on the platform in the top right in particular, the amount of solid ejecta again, which is being produced and which is being kind of shot off in different directions from the battery. And then in Toronto, the really relevant thing which I wanted to highlight here is then the subsequent involvement of the carriage of that piece of rolling stock from that fire as well. Okay, so we're starting to see with more and more frequency fires involving personal mobility devices, and quite significant fires involving personal mobility devices in a railway context, whether that's on a station platform or on passenger rolling stock. Now, I'm going to go back to the timeline which I showed you at the very, very start. And I want to revise this now based on what I've just shown you based on about the impact of personal mobility devices. And so what we're seeing with this is fire sizes which are approaching or exceeding a megawatt and a half. So even exceeding that larger fire which I showed you at the start for comparison. Growing very, very rapidly, producing jet flames, having a very abbreviated transition from smoke production to ignition, producing toxic gases, irritant gases, carcinogenic products. So they're producing things like hydrogen fluoride, hydrogen cyanide, polycyclic aromatic hydrocarbons as well, products which are lighter than air, which are heavier than air at the temperatures which are being produced as well. And then that will have impacts on their dispersion and distribution throughout carriages as well. And then they're also producing projectiles and solid particulates, ejecta, from those batteries as well, which form secondary ignition sources, which also ignite, potentially have the potential to ignite the furnishings and the linings inside of rolling stock, or even to ignite the gases which are produced as well. And if we look at the impact this actually has on the overall response to an incident, all right? So we've not changed the passenger displacement, the observation, or anything. What it's actually doing is it's moving our untenable conditions significantly earlier. So we're starting to have incidents occurring where the required response time is much, much shorter than the response time we're actually giving, all right? I'm using my terminology a little bit incorrectly there from a fire safety perspective, but what I'm trying to get across here is that the time that's available on board of the carriage to respond to the incident is actually significantly shorter than the time that we've given using the that we have available to us, given the response measures and the mitigation measures which we put in place in response to that as well. Okay, so that's really the key factor here, is that the time available to response has been compressed dramatically because of these fires. Now, all that I've shown you so far is actually fires going into thermal runaway and then igniting. But that's not the full story here. If we go back to the start of what I was explaining earlier, I was talking about the first mile, last mile mode of transport, or part of a first mile, last mile transport or commute into work. What that means is that most batteries are going to be transported at states of charge which are not 100%. So it's worthwhile looking as well at the consequences if we don't have 100% state of charge. So what I've got here is a composite video which shows batteries going into thermal runaway at different states of charge. The first row is 100%, the second row is 80%, the third row is 60%, and the bottom two rows are 40 and 30% states of charge. And what you can see here when I run this, these have all been lined up so that thermal runaway occurs at the same time. What you can see here is that while the higher states of charge do result in ignition, right? So the sorts of fires that we've already seen, the bottom two rows at the lower states of charge don't actually produce that solid and particulate ejecta from the cell, which means that they would need to come across another ignition source before they actually ignite. Now, that sounds positive until we think about the actual gas which is being produced. And what we've got here is the potential for quite large volumes of gases to be produced, which passengers potentially could end up being quite intimate with as well. Right, so and that will the gas, the nature of the gas, as well as the distribution of the gas, will actually vary if we don't have that ignition source as well. So quite different challenges based on the potential states of charge, which we don't have a lot of information about, as well as challenges to the response mitigation measures which we might have in place that would allow us to respond to our 1 kilogram newspaper fire at the start. So before I pass this back to Klaus, really what I want to leave you with is just an impression that the credible worst case fire in passenger rolling stock has changed, all right? So what I've presented to you hopefully today is persuaded you that lithium-ion battery fires have reduced the available time that we have to respond to incidents, and that creates new consequences for passenger safety, as well as for asset safety and asset design, and challenges risk management and incident response as they're currently relied on in trains, with the, I guess, resulting effect that current response and mitigation strategies aren't any longer demonstrably fit for purpose. And we do need data to be able to develop new management procedures, new response procedures, and to inform policy as it is, or as it should be in response to these incidents. So I'm going to stop sharing my screen and pass it back to Klaus, who will take you through the rest of the David. Technical documents.
That was excellent and beautifully illustrated and explanation of how the nature of the fire is completely different to what we're set up to deal with. Thank you so much. Share screen. Help me with this, David. PowerPoint.
Yep, PowerPoint.
Is that up?
That is up. We can't see a slide yet, Klaus. Yeah, we can see it. We can see the slide. No, we can see it now. Yep, you're good to go.
Yeah, yep. Yeah, so we've prepared the technical note, which is available from the ARISO website, and I think went out with the invite for the webinar. So the important things in the webinar, in the technical note that we've provided, is an explanation of what we agreed we knew about the nature of the fires and what we didn't know and what we needed to learn. And essentially what we needed to learn was the actual performance of a battery pack, not a single cell. So there's been lots of research on single cells. What hasn't happened is research on battery packs from a bike. And what we need to design to develop the model for the design fire, which we will all use in the industry to test our designs, is the characteristics of the design fire. So what we've proposed in the paper is testing on a real train with real e-bike batteries, and David will set up and measure toxicity and tenability and record the whole thing for us with his videos, as well as characteristics of the shape of the fire, et cetera, which will then help us all to retest and certify our arrangements. But we can also then use that to do simulations which inform what are the mitigations that are effective or not, as the case may be. So some of the discussions that we had which seemed to cut through this issue for us was there were lots of policy debates going on, but as a group we agreed these batteries will be in our environment, or potentially could be on our trains, even with whatever other measures might be applied. So what we took was a realistic approach, which is these batteries will appear in our railway, and we need to be able to understand how to mitigate their potential for creating fires and large amounts of smoke. So building off the technical paper we've developed with David and his group, the proposal to do the testing, and from the testing, we won't have to speculate on what the toxicity of the environment is. In 2 minutes, we'll know. And that will then inform the railway operations technical paper, which we're currently working on, which I'll talk to a little bit more. And then the third paper we'll produce is the emergency response. Because what we're looking at, and we do have emergency responders on our working group, and we all agree there isn't enough training material or information currently available for those people. And one of the key discussions that's going on around this topic in our group anyway is what information do the fire brigade and first responders need to safely approach the fire, and what equipment do they need to do any recoveries because of the extraordinary toxicity of the fire. So they're work in progress papers, but we don't do webinars here without sharing what we know. And discussions we're working on, and we'll finalize this once we have the technical results from the testing, is we see a need to do zonal risk assessment. So David will do the testing for us for battery failures in different parts of the train. So we can do zonal risk assessments on what are the hazards to the asset, what are the hazards to the passengers, what are the hazards to the crew, what are the hazards to the emergency services for a fire in that location on that train. And the dimensions of those hazards are train management. So that's the actual operation of the train. Remembering we could have ATO trains, we could have trains with the driver remote from the passengers. Then there's traffic management, which is the whole issue of I've got an emergency train with an urgent need to detrain. What are the other train traffic or corridor considerations that I might have in working out the appropriate response? Do I stop in a tunnel and let people unload? Do I drive on to the next station? If I pull up at the next station, am I parked next to another train? So do I expose a large group of people, etc.? Then the passenger safety issues, David's already explained quite well, and the asset challenge is real, and we'll do some more work on scoping that out. So just to be clear, we're not talking about these aren't largely new hazards to us. What is happening is these are all known hazards. We have mitigations. We have engineering standards for the construction of the trains. We have operating procedures for dealing with fire on trains. The whole issue with the papers that we're writing is all of our controls, our mitigations and defences are defeated by these battery fires. So that's the challenge. Some of the other things that we're looking at is carriage evacuation needs to occur less than 2 minutes. In my experience, that's unrealistic except for the most lightly loaded trains, and it's probably highly challenged in most suburban city trains. There's huge potential for passenger communications failure. That is the ability to communicate with passengers in this environment, A, because of panic, B, because the smoke will obscure all help points. The CCTVs that the crew might use to investigate will all be blocked or destroyed by the smoke. What we know from a recent incident is that even quite small, vape, trying to think of the right term, David, just where you have smoke coming out of the device, that contamination from those hydrocarbons and those fluoride hydrocarbons contaminates all the soft furnishings. So basically that whole carriage has to be changed out. So that has huge implications for asset management. We know that the temperature from examples in Australia, we know the temperature of the smoke is so hot, it destroys all the roof fittings, including, in some cases, the fittings that hold the roof itself up, but all the light fittings, all the handles that are up there. Our clear view is at this stage is staff should not attend the carriage. So we think the smoke is too toxic, and we believe the nature of the battery failure is so unpredictable, it's not safe for staff to attend the carriage at all. Emergency services are required with their PPE to enter the carriage. And after the event, we're pretty sure the testing will show that the train needs to be removed from service. So there'll be contamination in the carriage where the incident happened, but there's huge potential for contamination to occur in other carriages either side of the incident train. So at that, I might hand back to Sudha, I think on time.
Thank you, Klaus. You can stop sharing and...
Yep, doing that. Try again. How's that?
Yeah, thank you very much. Thanks very much, Klaus and David. Very clear presentation on the challenges that lithium fires in general, that as a transport industry is facing, but also specific for railway and what the challenges are. I am going to start off by asking a couple of questions. I'm trying to pick out the various questions that are coming through, but let me start with a few questions that I've got in place. We talk about, from what you shared, it's obviously almost a systemic review of everything that we know about the impact of fire and how it goes through. How effective is existing rolling stock detection, suppression, and ventilation systems when responding to lithium battery fire involving e-scooters and e-bikes? Is there any sort of control? Is there any effectiveness at all with the current setup that we already in place?
Really, there's two parts to the detection question. Please join in anywhere, David. The first part is the detectors will detect smoke, but what they won't do is detect the precursors to the failure of the battery. And that's what you need if you're going to have an effective response. Once the battery goes off, creates that hot smoke, you're in big trouble. So there's no warning time effectively with the smoke detectors that we have on the trains or are available to us at the moment. David?
Yeah, no, I think that's right. And it was something can you hear me now? It was something I was trying to get across as well, as the response time is significantly compressed. You're absolutely right. We don't have the opportunity for detection. What we do have, though, I think, which is possibly what we do have certainly is passengers who would have observed your newspaper fire would also be able to observe the start of a battery fire. But again, like, you know, the growth rate is so much faster with the battery fire that your ability to respond is significantly reduced.
And there's always the present danger of multiple cell defragmentation, which is a real risk. Basically, you're standing next to bullets going off.
Thank you for answering that. And the second question is, obviously this, you know, there's a lot of research needed to kind of understand this better, and which is very clearly articulated, and probably there are observations from international incidents to learn from, but we need to have some research in that area. In the interim, are the current controls sufficient, such as prevention of bringing these equipment on transport passenger? Is it sufficient? Are there anything else? Is there risk management processes that we can review to think about? What do we do in the interim while we are trying to work through some of the technical aspects and work through that? What are some of the things that we can consider?
I think it'd be difficult to answer that question very well, because we don't know what the controls are. I think there's a wide variety of what people are doing in the industry, but our conclusion was, even where the devices are banned, it's very we discussed it, and we believe that some people leave their bike at the railway station or at home and carry the battery, because that's the valuable bit, with them to work on the train. So the battery's still with them, even though the bike's left behind. So our view is these batteries we still need to account for them. We don't see an effective way for the staff to be 100% sure that they're not on the train.
Yeah, I think that's right, and I think you know, it extends possibly beyond just the impact of personal mobility devices. It's not just your e-ridables; it's also things like laptops or tools, which people are carrying onto the train as well for work. So it goes beyond this.
Thank you. I'm going to quickly, there are a couple of few questions coming from, I'm going to read a couple of them. Batteries obviously ever growing. Do you have any thoughts on passenger behavior, how this might be adjusted? That is, stop people videoing fires and getting to places of safety.
No.
How do you feel this type of battery? Yeah.
I'm glad that's raised, because, you know, I really believe this is one of those cases where we need to train our passengers to understand this is no time for voyeurism, and part of that education has to be helping them to understand this is a really dangerous situation which they need to evacuate from, and help other passengers evacuate from. I think there is a public education message to be had here. I think the video of the scooters David had in people's apartments, a really good example of, you know, what could be occurring in a crowded passenger train, and it's no time to do anything but escape. And we don't always see that, and I think it's a public education thing that should be occurring.
Another question: how do you feel this type of battery might challenge current ways of dealing with fire? That is, go to next place of safety for removal. What is the fire service view of their revised role?
I think,
yeah, David.
Well, oh no, I was just going to say, I mean, I wouldn't want to speak for the fire services here at all. I'd be interested in hearing from anybody who's online who is from the fire services as to what their opinion is. But I think the reality is as well that fire services are not going to be on the train before the train has the opportunity to stop. So the passengers and the onboard crew are going to have to do something to mitigate the consequences of this fire until such time as they're able to detrain the passengers. So I don't think that changes in this case.
Yeah, so the way I understood the question, Sudha, and clarify if I've missed it, the question is, do you move to a place of relative safety? So that's not a place of ultimate safety if you've got a battery fire on a train. So now relative safety is, of course, the next carriage, but it could also mean if you're on a crowded commuter, pulling up in a tunnel and letting the passengers evacuate into the tunnel, which is also highly undesirable in my experience as an operator. We will still have serious injuries, but given the nature of the battery fire, it might be highly desirable and the lesser of the two evils.
With modern train design as well, doing away with separation between rolling stock as well, so continuity, then you don't have the opportunity to move to a place which is completely separate and isolated from the location of the incident.
Yeah.
That's a related question we've got in here. Someone asked, do you foresee this information and research work will start to impact the design of passenger trains in the future, and how do we approach that? So that's a question asked here as well.
Yes, well, I think we hadn't realised how we'd moved ahead until the Underwriters Lab and the UIC representatives came to one of our meetings and said, you are leading the testing and the thinking about how to respond to this in the world. And they're waiting for us to do the full-scale testing so that we can have some objective data to say we need to rethink about how we mitigate these. Yeah, so I think that was an eye-opener for us as well.
Yeah.
That's a really good endorsement, I think, for the work that you guys are doing. So fantastic effort. Here's a question around the gases. What specific types of gases are being produced? What are the likely health impacts versus exposure time? Anything?
Well, they're mostly hydrocarbons and hydrofluoric acid and lithium and fluoride hydrocarbons. Basically, lots and lots of nasties. In a very hot gas. But David, over to you.
Yeah, no, that's fine. I mean, it's light hydrocarbons as well as hydrogen fluoride is really the most important one, I think, which we've observed in testing. It's a very nasty stuff to either get on you, and it's a very nasty gas to either get on you or to inhale as well, which can lead to very significant health impacts as well. There are a host of other gases as well. So I talked about polycyclic aromatic hydrocarbons as well, which can be carcinogenic, which are produced by this. Obviously, things like your exposure time could be relatively short, but if you're intimate with the device, once it starts to go into thermal runaway, then you could be breathing in quite a significant quantity as well for a short period of time.
Yeah.
Thank you, David. For your timeline of passenger crew vehicle response, the timeline appear conservative. I think it's one of your diagrams, David. Considering first mile, last mile transport and the peak occupancies generally occur in metro, how would this diagram look considering 2 to 3 minutes travel between stations or less?
Yeah, that's a great question. And obviously the timeline was intended to be illustrative of what could be a worst case in terms of the time to stop a train. But even bearing that in mind, if you've got 2 to 3 minutes travel time between stations, and then you've got the time taken to detrain all of the occupants from of a train during peak hours, during rush hour as well, you're still going to have several minutes, which is longer than the time to untenable conditions is likely to be, given the nature of this fire. So I agree, it's conservative. It may be truncated a little bit, but it's still likely to be longer than the time that you actually have before untenable conditions.
Yeah, and we'll know that from the testing.
Absolutely, yeah.
There are quite a few questions coming through, so I'm going to do as many as I possibly can before we finish.
Okay.
Are there any other countries that are ahead of the game and have introduced specific regulations or infrastructure changes to address lithium battery fire risks on trains, and what can Australia learn from them?
There was actually a report that was done by GHD. I did mention this when I was talking for ONSER, which reviewed internationally what responses have been taken. There's a lot of diversity in terms of measures which are proposed, but there's no evidence certainly to my understanding, there is no evidence to support any of those. There's no evidence to suggest that they're actually effective in terms of dealing with these hazards. The work that Klaus has mentioned, which we're planning on doing, is really world leading in that respect, in terms of gathering the data to support whatever decisions are taken with regards to design or changes to incident management and incident response.
Thank you, David. Here's another one. Has much work been done on causes initiation events on the lithium battery fires? It seems that charging, either overcharging or charging a damaged cell, is the common cause of thermal runaway. Can controlling this help meaningfully reduce the likelihood of these events?
Well, first I would say that the group, David will have an answer, but the group did not agree on some of the papers that we reviewed on this topic. We felt that they were weakly based in research. And if you think about it, you need to follow up incidents, and the device that you want to inspect gets destroyed. I mean, really destroyed, like at 1,000 degrees. So it's very hard to determine in some of these cases what was the actual root cause. But over to you, David.
Yeah, no, I was just going to say, I think this is a great question. And there's a lot that could be said on this topic. So if I remember correctly, the statistics from Fire Rescue New South Wales do suggest that some of the vehicles, some of the devices which go into thermal runaway were either charging or had recently been charged, but it's absolutely not a controlling factor. It's not a defining factor, rather, as to the risk of thermal runaway. The potential for collision or damage leading to thermal runaway several days, potentially, or hours, or whatever down the line from when that damage occurs is also there as well. So, if you control charging, then you could potentially reduce the likelihood marginally, but I think that it still remains a foreseeable scenario that you will have to deal with the consequences of, because of the other factors which could lead to it.
Yeah.
Very good. And I'll probably finish with these final questions. There are several questions. We probably need to take it on note and probably respond back another time and create some answers. Have you ever considered all the engineering controls implemented in the device design? What are the statistics of these incidents involving devices with BMS or cells with CIDs versus nothing at all? What level of controls are required to reduce the risk of thermal runaway occurring at the device level? That's a technical one. I'll throw it to you, David.
Yeah, okay. No, this is another really good question. There are a lot of really good questions, and thank you all for this as well. So it's easiest to respond, I think, to BMS. The BMS is there as a load leveling mechanism, principally, which manages the voltage across the cells during charging, as well as discharging. It does monitor, well, some of them will monitor temperature, and some of them will be advanced enough that they'll also isolate individual cells. I think the issue with personal mobility devices, though, is that isolating cells isn't going to prevent one which is already heating from going into thermal runaway. And you have other factors which could contribute to thermal runaway, which you mentioned before, including collision or external damage to the cell, or even factors associated with charging or other forms of abuse, which wouldn't be mitigated by the presence of any other devices within the cell. So I agree with you, Ben, as well, who's asked this question. I think that some of these devices, some of these factors could contribute to reducing the likelihood, but I don't think that they eliminate the hazard at all. Really great questions. Thank you.
We run out of time, David. I will compile those questions as well for the work group to consider and think about and respond back. But thank you again, Klaus and David, for providing your time to present today. And thanks everyone for participating. You will continue to hear about the project that we are doing from our website and the papers that are coming up, and the research activity. We'll continue to update that through our website. Once again, thank you for your participation.